In this video, we will be expanding on our previous discussion of the three-dimensional nature of molecules to look at how we can represent these three-dimensional structures using our Lewis dot structure representations. First of all, drawing molecules, which are three-dimensional in nature, to show their dimensionality on paper, which is a two-dimensional medium, can be difficult. That is, unless we have a common convention that is mutually agreed upon for conveying the three-dimensional information. The way that we will draw three-dimensional representations on paper is as follows. By convention, the central atom is put in the plane of the paper. Then you will put as many atoms as possible on that same plane and indicate them with a straight line. So a straight line will indicate things that are lying on the paper. Atoms in front of the plane, or those that are coming out of the page, will be represented with a solid wedge, and atoms that are going into the page or are behind the plane will be represented with a hashed wedge. The convention is typically having the central atom at the small point of the wedge and the atom that you wish to represent as being either out of the plane or into the plane being at the large end of the wedge. However, for the hashed wedge, sometimes you will see it where the central atom is on the large side and the atom that is going out of the paper is on the small side, both of which are reasonable. So looking at our three-dimensional structures, for a linear molecule, everything can fit on the plane. So we have our central atom on the plane, and then we will attach our two outside atoms, or the two atoms that are bound to the central atom, with straight lines, because everything can be in the plane. Similarly, for trigonal planar, because it is a plane, hence the name planar, everything can lay on the plane of the paper. Because everything is on the plane of the paper, all the bonds are represented with solid lines. Bent geometries, for the same reason as the trigonal planar, will also have all the atoms lying on the plane of the paper, and so all the bonds are represented with straight lines. Once we get to four things attached to the central atom, our tetrahedral arrangement, this is when we need to start worrying about three-dimensional representations. We put our central atom on the plane of the paper, and then we can select two of our groups that are attached to that central atom to lie on the paper. The other two, because tetrahedral is a three-dimensional structure, one will have to go into the plane of the paper, this one here represented with a dashed wedge, and the other one will be coming out of the paper towards you. That would be represented by the solid wedge. Trigonal pyramidal, you would replace your vertical one here that you had with your tetrahedral. This is now where your lone pair are, and you'd have a solid line, a dashed wedge, and a solid wedge. For trigonal bipyramidal, it is possible to have both of your axial atoms and one of your equatorial lying on the plane of the paper, with your central atom also on the plane of the paper, but then you will have one atom going away from you, going into the plane of the paper, which is represented with your hashed wedge, and one that is coming out towards you, one that is represented by the solid wedge. For seesaw, you would just replace your solid line here with a blank spot, and so you would be left with something that looks like this. Octahedral, because of the nature of octahedral, you would have your central atom on the plane of the paper, your two axial being vertical, and then you would represent two of your groups going into the paper and two coming out. This is as opposed to having two lines horizontally and then a hash wedge going out and a solid wedge coming in. The hash wedges and solid wedges aren't typically used for something coming straight out or straight back, which is why you wouldn't use solid lines left and right and a single set of hashed and solid wedges. Instead, you go with this sort of a representation. For square planar, because everything falls within a plane, you would represent it with your central atom and then solid lines for each one of your groups. Many of the molecules that you will work with, particularly in a biological setting, will be larger structures that have many interior atoms. You can think of those interior atoms as their own individual central atoms. So when we're talking about the geometry of a molecule, we can say that at a particular site we have a particular geometry. So for example, our NH2 group here, this nitrogen has a trigonal pyramidal arrangement. This carbon has 4 things bound to it, and so it will have a tetrahedral arrangement. The carbon here, which is double bound to an oxygen, single bound to another one, represented here, will have a trigonal planar arrangement, and then this last oxygen will be bent. So our discussion of three-dimensional structures is not just for atoms that only have one central atom, but when they're strung along in a chain, you can have multiple, quote, central atoms, each with its own local structure. Those local structures will dictate how the molecule overall will interact with other molecules.